14D. So ordered selections with identical elements. Okay, so what that means is that I'm going to be giving you a word like this one here, feet, and you can see that there is two E's in there. Okay, it's not that funny.
I don't know. I think they're both died.
So normally, if I wanted to arrange 4 letters, we would just go 4 factorial and get 24. However, it is not going to be that for this question. Now, the reason why is because if I take the very first arrangement, which I'll just use feet, those 2 E's in there, it doesn't matter which E comes first and I still get the word feet. Okay, those 2 E's in there are actually a double up. Okay, and same with if I put F-E-T-E, there would be 2 options of that with the E swapped around, and each of those options would be being counted if I just did 4 factorial. Okay, so each of these ones here, you could just write in here, they have duplicates. Whenever there is a repeated letter or number, if we were doing numbers, then there is going to be duplicates when you're trying to do your arrangements. So this is how we're going to attack it in this next part here. Similarly, finding the number of possible words that can be made using all the letters of the word acacia. So that's a good word because it has 2 C's and 3 A's. Okay? If all the letters were distinct from each other, there is 1, 2, 3, 4, 5, 6 letters. So if they were all distinct, we would just do 6 factorial possible permutations there. Order is important, hence I can use that word permutation. Okay, however, the 2 C's can be interchanged without changing the word. So we have overcounted by a factor of 2 factorial, which as we know is equal to 2, right? So sometimes we just write 2 factorial as 2 because we know it's the same. In the same way, the 3 A's can be interchanged without changing the word. So for the A's, we have overcounted by a factor of 3 factorial, which is equal to 6. So the total number of ways, if I was trying to arrange the different letters in the word acacia, you would start with the 6 factorial, the total, not take away, it's divide. You divide by the repeating letters. So I divide by the extra 2 factorial for the 2 C's and the 3 factorial for the 3 C's. Okay, you divide out the repeating letters and don't forget the factorial on them. Now, when you type that in, even though I have written the 2 factorial and the 3 factorial next to each other, your calculator, I believe, will need a times in between there. Okay, otherwise it won't know what to do. So type that one in. 6 factorial over 2 factorial times 3 factorial equals. Did anyone try it without the times?
And then you get syntax error.
Yeah. Yeah.
Syntax error.
Yeah. So without the times, it will give you a syntax error, so you need to put a times in there. Yeah. So there is 60 ways to arrange the letters of the word acacia. So then here is the formula version of that. In any word where we're trying to arrange the different letters, N stands for the total number of letters in the word, and we divide by the repeating letters, however many of them are. If there's only one repeating letter, it would just be whatever the first letter repeating, factorial. Times by if there's a second number repeating, a third one repeating, however many things are repeating go on the bottom, okay? And that's our rule for today. Well, example time. 1A. How many different 8-letter words are possible using the letters of the word syllabus? Okay, so syllabus, we've got S and S, and we've got L and L. So we've got 2 repeating letters. Sometimes it helps to write it down. So I'm going to write here, I've got 2 S's. That's a bit of a weird thing to write, 2 S's. Is that bad English to write it like that? Anyway, 2 S's and 2 L's. Okay, I'm just writing down. I've noticed that I've got some repeating things here. So all I have to do, oh good, thank you. All I have to do is count up how many letters I have. Actually, it already tells me. I have 8-letter word there. So 8 factorial is going to go on the top, divided by the repeating letters. So I have 2 S's repeating times the 2 L's repeating. What did you get, Tori?
Times them.
How many is that?
1,080.
10,080?
10,000.
Yeah. But okay, now obviously, any of the previous things that we've learnt could also come into play here. Like in part B, we now want to find how many ways we can arrange those letters if the 2 S's have to be together. So this is where we're making things into an extra group here. I think we did this last lesson. So yeah, so if the 2 S's are becoming one group, that means I now only have 7 groups that I'm arranging, correct?
Yeah.
Yes? So 7 factorial. Now normally if I have a group with 2 things in it, I would times it by 2 factorial. But because they're S's and SS is the same as an SS, if the things in that group are the same, it's not, you don't times it by 2, you're putting, you see how that's a double up if you do that?
Oh, yeah.
Okay.
Just divide by 2.
So all we have to do is divide by our 2 L's, because they're still floating around separate in there. So our 2 L's divided by 2 factorial.
2,520.
Correct.
You're welcome, Ben.
And situation number 3 for part C. How many of these words have the 2 L's at the beginning and the end? So we lock the L at the beginning, the L at the end. How many letters are in between that? 6. Good. So there's 6 factorial letters left to arrange. Do we have any repeating letters that we haven't used yet?
S.
The S's. So I'm going to have to divide by the 2 factorial. Now we're doing that kind of fast because you guys are giving me answers so quickly. I'm hoping it all makes sense.
360.
It all makes sense?
Yeah.
Wonderful. Next page. Example 2. At the front of a building, there are 5 garage doors. 2 of the doors are to be painted red, 1 is to be green, 1 is to be blue, and 1 is to be orange. Basically, what you can see, it doesn't really matter what the colours are. We have different garage doors, but 2 of them are the same colour. Okay? Ideas. There was 5 garage doors, so to put 5 of them in order, yes. 5 factorial, yes. Good. But because 2 of them are the same colour, there's my repeating. I divide by 2 factorial. 60. Okay, part B. How many possible arrangements are there for the colours on the doors if the 2 red doors are next to each other? So they become a group.
Factorial.
I only have 4 groups now. Don't divide it by anything though, because my 2 repeating colours are next to each other in a group. They're no longer, I'm no longer counting them twice, right? Yes?
Is it because they're they're the same that we don't times?
That's
by
right.
2?
Yes, because they're the same colour. Correct.
So if they're not the same colour, but they have to be together.
Yeah. So when we did these before, we had 2 people. And so, okay, so it's different if Jess and Tori are sitting next to each other, the order that they sit in. But when they're the same colour, it doesn't matter if it's red, red or red, red. That's the same thing.
Yeah.
Okay, so we don't times by that extra.
There are only 2 options.
Okay, so this is pretty much the same thing as what we were just doing. It's just an extra special case here. When there are only 2 options, the concept of counting with identical elements becomes particularly important when there are only 2 options, as will be explored in this next chapter. Suppose that an N letter word, so that's how many letters are in the word, N is the number of letters in the word, consists of R number of Y's, Y's, and R minus N, N's. Okay, so it's really bad English there, isn't it? So for example, it could be, not a highlighter, it could be, I don't know why you'd have a word with Y's and N's in it, but anyway, Y, N, Y, Y. Okay, so knowing that there's 4 letters that in that word that I've made up, because I've said that 3 of them are Y's, there's 4 minus 3 N's, which makes 1. There's 1, right? So it's like, because there's only 2 options in that word. There's only 2 options in that word. That's what the thing was. There's only 2 options. Okay, so if one of them has to have 3, then the other one has to have 4 minus 3. Okay, so when then the number of distinct possible words is n factorial over r factorial n minus r factorial. Does that formula look familiar?
Yeah.
What does it look like?
Different one.
Yeah,
Combination.
it's the combination. Okay, that is actually the combination formula. Okay, so if you only got two options, all you really need to do is go, well, how many y's do I want? It's like saying I have four things. If I have four things, I would just go 4C3. If I just focus on one of the letters, 4C3, and obviously the other one has to be a y. There's no choice left then because I've only got those two options,
So
right?
Does 4C3 give you the same answer?
I didn't actually give an answer for that one, but yes, it will.
Yeah.
Yes. All right, so imagine that Mrs. Kirby, because I think she made up this question a few years back, has 4 identical chemistry booklets and 6 identical maths textbooks in anticipation of more students joining her class. In how many ways can the books be arranged on the bookshelf if there is no way of distinguishing between the identical texts? Okay, so this is the two options. There's only two options. There's chemistry books and there's a maths book, right? So altogether, how many books are there? Sorry, Isaac, yes?
Like, are the books separate, so all the chemistry books together and all the maths books together?
No, it doesn't say that. It just says how many ways can I arrange these books on the shelf. They don't have to stay in groups. No, but we've
10
got,
books
there's 10 factorial.
It's 10 factorial over.
divided by 4 factorial and 6 factorial.
Yes. So there's the 4 repeating chemistry books. And if we could, as I said, these are very similar to what the last question was. There were 6 repeating, maths books as well. So 6 factorial for that. But it also works with that formula there. If I knew that there was 4 chemistry books, then I would do 10 minus 4, which gives me 6. It works both ways if you had either one of those. Okay, so that makes 210 different ways of arranging those books on a shelf. Cool. All right, using cases. Many counting problems are too complicated to be analysed completely by a single box diagram. In such situations, it is necessary to consider each case separately. Okay? So, this is what a question like that is going to look like. How many 6-letter words can be made from the letters of the word Glenelg? Now, first of all, Glenelg, 1, 2, 3, 4, 5, 6, 7. There is, oh yeah, cool, it is. There is 7 letters there. Okay, I've got 7 letters. It's the first thing we notice. And I need to put 6 of them in order. What's up?
I'll tell you later.
You'll tell me later? Okay. Okay. So, the question is, and this is why we need cases, is which letter is going to get left out? Okay? And we can't really do that in one calculation. So we have to do each possible case separately. So first of all, we're going to pretend that we're going to choose the G. If the G is left out, so the G is omitted, okay, G is left out, how many repeating letters do I have in there? I've got, I've only got 1 G now. How about the L's? There's 2 L's.
2 L's, 2 E's.
2 L's and 2 E's is what I still have. I only have one of the other ones, right? So then if I use the formula, I've got, how many letters am I arranging? 6 factorial, good, because I'm only wanting 6 of them. And I've got 2 L's and I've got 2 E's that are being repeated. So that is 180 ways if the G is the one that's left out.
What do you mean by left out?
Because we have 7 letters, we don't know which of the 1 letters, because we've got to put 6 of them in order, but we don't know which 6. So we're going to change each of the possibilities. We're going to do each. It could be a G, an L, an E, or an N because they're the different letters that are in that word. So we're going to go through and look at each case separately. If that letter's left out, it's that many ways. If that one's left out, it's that many ways.
Oh, because asking for how many 6-letter words.
Words altogether.
Okay.
Yeah.
Yeah.
Okay, so let's now do the L is omitted. So if 1 L is omitted, okay, because you only can get rid of 1 letter, we then only have 1 L left, but...
2 G's and 2 E's.
That's right. 2 G's and 2 E's, which means it's going to be the same as the last one. All right, so that is 6 factorial again over 2 factorial, 2 factorial, so 180 again. What about is if the E is left out?
Same thing.
It is going to be the same again because I'll keep writing on my working out here. I'm going to have 2 L's and then I would have 2 G's. So it'll be 6 factorial again over 2 factorial, 180. The last one is different.
Yes.
If the n is omitted,
6 divided by 2 factorial, 2 factorial, 2 factorial.
yeah, because I've got 2 L's, I've got 2 E's, and I've got 2 G's. Because the n, there was only ever one of those to begin with. Okay? So there is 6 factorial, I just said, over 2 factorial, 2 factorial, 2 factorial, which is only 90 ways. So once you have gone through each of the possibilities, all we have to do is add those numbers together at the end. So our total is, I'm just going to go 3 lots of 180 plus that 90 is 630 ways of making a 6-letter word from the 7 letters that we were given with repeating letters. Fun, right?
Example 5.
All right, our new question, example 5. I picked this one straight out of your textbook. I think it was question 12. So if you look at the questions down the bottom, I picked one right towards the end. I was trying to pick one that will hopefully be the difficulty towards the end. So it says, containers are identified by a row of coloured dots on their lids. The colours are yellow, green, and purple. In how many arrangements are there if there are to be no more than 3 yellow dots, no more than 2 green dots, and no more than 1 purple dot? I'm going to write that. I can have 3 yellow, I can have 2 green, and I can have 1 purple. I can't go any more than that. That's 6 dots, right?
Yeah.
That's 6. I can't have 4 yellow and take one of the other ones down. I would have to use exactly those colours, wouldn't I? If I wanted 6 dots, I would have to use 3 yellow, 2 green, and 1 purple, right? Okay. How am I going to count those? There is 6 dots, so 6 factorial.
Divide by 3 factorial.
Divide by the repeating colours, that's right. 3 factorial for the 3 yellows and 2 factorial for the 2 greens. Yeah, that one's the easy part.
60.
Okay, now that was the easy one because I used I had exactly 6 and I had to use exactly 6. But it's always when there's less, okay? I've got choices of things that I can get rid of, like in part B. What are the number of different codes possible if only 5 dots are used?
We have to do the
So,
Y's and...
yeah, so I could choose one of those colours to leave off. So I could leave out a yellow, I could leave out a green, or I could leave off the purple, and I would have 5 dots, right?
Yeah.
So let's do those as a case for each one of those 3 cases. So the first one is going to be 2 yellow, 2 green. I'm going to leave off one of the yellows to start with. 2 yellows, 2 green, and 1 purple. If that was my 5-dot combination, I would do 5 factorial. There's only 5 dots now that I'm using. Over, I've got 2 yellows and 2 greens. Yeah?
Yeah.
So then we go to our next option. Okay, I'm going to keep the 3 yellows this time, but I'm going to get rid of one of the greens instead. So I'd have 1 green and 1 purple. So I'd have 5 dots still, so 5 factorial. But there's only the 3 repeating yellows. The other 2 colours aren't repeating. That's only 20 ways of doing it that way.
Wait, what?
Because 5 factorial divided by 3 factorial is
yeah.
only 20. And finally, I could leave off the purple. So I could have 3 yellows and I could have 2 greens and just have no purple. I don't have to have any purple. So that again is 5 dots, but I have 3 repeating yellows and 2 repeating greens. That equals 10. Okay, so all I have to do is add those together. 30 plus 20 plus 10 means that there is 60 different ways, and it's a bit of a coincidence there was 60 for the first one as well. It is a coincidence. Okay, there's 60 different ways that you could make a 5-dot colour combination from the yellow, green and purple options that we had.
Yeah.
Okay, that's it.
Okay.